Okay, we will get started. I hope you guys are doing well. Hope you guys are staying healthy. And so this will be kind of our first real lecture of real actual content, and we will get started here. Okay, so I want to just start off with models and machine learning. Okay, so we're going to cover some basic machine learning stuff here, and um, and so let's just talk about this. What is machine learning in the first place? And if you check out Wikipedia, it's got this. There's a whole bunch of articles that you can read. But we're going to say machine learning is the. This is what it says is the scientific study of algorithms and statistical models that computer systems use to effectively perform a specific task without explicit instructions, relying on patterns and inference instead. Okay, so there's a bit to unpack there. But the idea here is that we provide the computer with some data, all right? And we want to fit a model to it. Now, as people, as humans and researchers, we still have to make a whole bunch of decisions, right? We have to decide what kind of model to use, um, certain things about that model. But then a lot of the other decisions are going to be guided by the data and the algorithms, right? So what parameters to use, all of that, those decisions that are made by the algorithm, okay, that's this part where it says perform a task without using explicit instructions, meaning that we didn't tell it to use the number 3, but we said figure out what number to use there, okay? That part is the machine learning part of it, okay? Where we are not specifically saying these are exactly the values you have to use, but the algorithm will figure that out, okay? Um, but people still have to make a lot of the decisions, okay? Sometimes people think of machine learning as this magical tool, and it's not, right? Neural networks are very powerful. You can do all sorts of stuff with them, but you can't just throw a neural network at some problem and say, solve it and figure it out, okay? There's a lot that needs to be done and a lot of decisions that a person has to make um, about this, okay? All right, so the term model is something that gets thrown around a lot. And, um, and so, let's just talk about what is a model, what is a statistical model when we're talking about something like that. And we can say, just in general, a model is a simplified representation of something complex. So here I've got a picture of a model airplane, okay? It's a toy version of the airplane, and it's a simplified representation of the very complicated real airplane, right? Airplanes in real life are very complicated, all sorts of parts working together. And this is just a toy simplified version of it, okay? And so when we talk about a statistical model is a simplified toy, or not toy, but simplified representation of some kind of complex thing, complex process that exists in the real world, and that complex process in the real world generates data, right? So you can think of, in the real world, we might wonder what is responsible for how tall a person ends up becoming, right? So if you say how tall will this person be when they grow up, there's all sorts of things that can go in to influence that, right? Their genetics, um, their nutritional factors, environmental factors, all sorts of different things go into ultimately determining um, someone's height, okay? And that's complicated. But we can simplify it and just say, you know what? All of that genetic stuff, there's all sorts of, probably this gene and this gene and this gene and this gene are responsible. Let's just simplify it. Let's just say, you know what? How tall were the parents? How tall was the mother? How tall was the father? Or whatever it is. We're going to take a look at that, and that will help us make a prediction, okay? Very simplified version of something that's happening, right? So when we talk about the process that generates data in the real world, that's going to be complex. That's going to have a whole bunch of different factors working to determine the outcome. And the statistical model is going to be a simplified version, right? It's only going to look at a few of the variables, okay? And there's always going to be an error term to kind of account for everything else. All of the stuff that we can't explain, that's going to go into the error term. All right. So one sentence that we often use in statistics is this phrase: all models are wrong, but some are useful. Okay, all models are wrong, but some are useful. All right, and that models will not make predictions perfectly, and there's always going to be some aspect that is not accounted for in the model, but they still can be useful in helping us understand. Oh, you know what? Before I forget, let me give you the answer to the first attendance quiz question. The first attendance quiz question answer is A as an apple. A as an apple. That's going to be the answer to the first attendance quiz question. Okay, so when we use a model, okay, there are generally two goals that we can incorporate or pursue, right? One is we can try to use a model to help us make predictions. So you've got inputs, and you want to try to predict the the output, and you've got certain models that are good for that. Neural networks are really, really good at making predictions. Okay, and then there are other models that are more useful to help us gain an understanding of the relationships between variables. Things like linear regression. Linear regression is highly interpretable, right? You can easily say, when we change this, it's going to affect the output by this much. Linear regression, easy to interpret, okay? And these two goals sometimes work together, sometimes they are in conflict, okay? And you might have to choose one over the other. You might have to say, it's more important for me to make better predictions, and I'm willing to give up interpretability. Or you might say, you know what, it's more important for me to understand the relationships, and I'm okay to give up some accuracy here, right? So if you choose linear regression, you're going to have high interpretability. The predictions are generally pretty good, pretty okay, but there's going to be probably other models that can do an even better job of making predictions. But making those better predictions comes with the sacrifice of no longer being able to understand everything quite as easily, right? So sometimes we have to choose to prioritize one of these goals over the other. All right, so we're going to take a look at some data from the textbook, okay? And this data comes from the Olympics. It's going to be the 100 meters men's race. Okay, so it's the track and field event where they're running, and a lot of times the winner of this thing is called the fastest man in the world or something like that. And there are a whole bunch of factors that are going to factor into the winning time. Okay. But one thing, as far as a simple model goes, is that there's just been a relationship that over time, the gold medal winning time has gotten faster and faster. Okay, when the Olympics were first held in like 1896 or whatever, okay, around 1900, the winning time was somewhere around 11, 12 seconds. Okay, 1896 it was 12 seconds. I think it was because they didn't have accurate stopwatches, so they were not able to record things to like the thousandth of a second that we are able to do today. And in 1900 the winning time was 11 seconds, right? I mean, so that's fast, but today a lot of people can run the 100 meters in, I don't know about a lot, but 11 seconds would not get you qualified for the Olympics type of thing. But as time has gone on, the gold medal time has gone under 10 seconds, and it's now definitely under 10 seconds to win the gold medal. And so there's just kind of this relationship that as time has gone on, the gold medal time has gotten lower and lower, right? There's lots of different factors, but if we simplify the picture, the world, down to just this, we can say, okay, there seems to be a relationship between year and time, right? So we're going to say, race times have gotten faster over time, right? And so if we know the year that the Olympic Games took place, we might be able to make some kind of prediction for the winning race time. It's not going to be accurate 100%, but it's going to be better than if we didn't know what year it was at all. Okay. When we use a linear model, that implies that how much we adjust our prediction is going to remain the same, is going to be a constant for all the values through time, right? So if from 1920 to 1924, if we say the time went down by 0.05 seconds, we're also going to say between the year 2000 and the year 2004, the time also went down 0.05 seconds, okay? Obviously, we can't use this for predicting things in the far future, right? Because in the distant future, that would imply we could eventually reach negative time for a race, which doesn't make any sense. But still, at least for the data that we've collected, this kind of model could be useful, okay? And so when we want to fit the model, in this case, for a linear regression model, we have two parameters. We have a slope and we have an intercept where it crosses the y-axis, right? And so when we talk about fitting a model, it's just the process of estimating those model parameters. In our case, fitting the model means figuring out what slope to use and what intercept to use. When we talk about fitting a neural network, it just means, so when you define a neural network, there's going to be a whole bunch of parameters, not slope and intercept, but a bunch of different like weight parameters and stuff like that. And it's just a matter of figuring out what those weights should be. When you're talking about fitting some other kind of model, it's going to be just what parameters should I use? Okay, what are the estimates I should use? Okay, and so we want to pick the values of these parameters, the slope and the intercept, so that the resulting model, the resulting line, does a good job of fitting the data. Okay, and so how we define the best, okay, when we want the best parameter estimates, how we define this word best is very important, and it's going to be carried out through our choice of an objective function. So what you choose to be your objective function is going to be related to what you decide is the word, how you define the word best, okay? So for linear regression, best means the model, the fitted line that minimizes the total squares of the residuals, okay? We're looking to minimize the total squares of the residuals. I know this is a review for you guys. And we said, you know, the residual is the difference between the actual value, your y sub n, and your predicted value, y hat sub n, okay? So the actual value minus the predicted value, that's your residual. We're gonna square that residual and we're gonna sum them up, okay? And so the sum of the squared residuals, that's our RSS, or that's the total squares of the residuals. This, we're going to say, the line that makes our y hats a certain value that minimizes this thing, that's going to be the best line. We want to pick the slope and the intercept so that when we have our y hat values, this quantity is as small as possible. Okay, that's going to be our objective function. In this case, our objective function is a value that we want to minimize. Okay, we want to minimize this. So this is also called a loss function or a cost function. Loss function or cost function because generally you want to minimize your losses, you want to minimize your costs, and so we're going to call this a loss or a cost function. Okay, I'm thinking this is all very familiar to you guys because I think you guys are all very familiar with linear regression, right? Okay, and so many different machine learning models, okay, including linear regression, fit parameters by trying to minimize or maximize some objective function, okay? So linear regression technically counts as a machine learning model. I would not go about bragging and say I can do machine learning if the only thing you can do is linear regression, but technically linear regression counts as a machine learning model. And all of these things try to fit parameters by, or not all, but a lot of them try to fit parameters by minimizing or maximizing some objective functions. And because we're trying to minimize or maximize a function, we can often call a lot of these things optimization problems, okay? So we can reframe a lot of these machine learning problems as optimization problems, okay? And I know linear regression is review for you, but we're going to start here because I want to cover a lot of these important concepts in machine learning, things like cross-validation and train test split and shrinkage and all of that. It works well in the context of machine learning and linear regression. All right, I'm going to try to match the textbook notation. Okay, I know not all of you have the textbook yet. I encourage you to get your hands on a copy of the textbook. It's a very good book. This is what the print version looks like. I know stuff is floating around on the internet, and my request is that you do not post links to copyright infringing materials onto the course campus wire. I want to kind of keep the course campus wire kind of clean and above reproach there. So what you guys do is up to you, but please don't put links and stuff to like that on the course campus wire. So but anyway, it's a good textbook, and I'm going to try to match the notation. Okay, and so in the textbook, instead of calling the actual values y, the actual values are denoted with t sub n. Okay, so someone asking, is it okay if we have the first edition of the textbook, or do we need to have the second edition? I don't know what's in the difference between the first and the second edition, so I can't answer that question. I think the second edition is missing, or first edition is missing principal components analysis. Okay, and I don't even get to cover all of the chapters in the textbook in our 10-week course. So so we do miss some stuff, but I think the first edition is missing PCA. I'm not sure about the. I haven't seen the first edition, so I can't answer that. But I think that's what somebody told me. So okay, but anyway, in the textbook, the actual values are denoted with a t rather than a y. Okay, and then as far as the slope and intercept get the letters W0 and W1. Okay, so the intercept is W0, the slope is W1. Okay, and the value predicted. So if you input xn and you say, what does the function predict? What does our model predict for xn? That's going to be given by this function f of xn at w with parameter values W0 and W1. Okay, the book also uses the mean squared error. So rather than the total sum of squares, we're doing the mean squared error. So we take the total sum of squares and divide by 1 over n. Okay, so basically we're going to rewrite our mean squared error as 1 over n sum of yn minus y hat n. We replace the yn with t sub n, and we replace the y hat sub n with this f of xn, where the values of with the values W0 and W1. Okay, so this is where we are. We can rewrite the loss function as that. Okay. A side note, a lot of times you'll hear the term RMSE, root mean squared error, right? And you're going to talk about, oh, when we ran this model, we got an RMSE of 1.273. Okay, and you go, oh, all right, is that good? So RMSE is basically mean squared error, this thing, okay? But you take the square root of it. And the reason why you might want to take the square root of it is that let's say your measurements are in centimeters, okay? Your residuals will be the difference between the actual and the predicted, and so your difference will also be in centimeters. But your squared residual will be, the units there will be centimeters squared. And so dealing in squared units could be hard, and your total mean squared error is going to be in centimeters squared. And so taking the square root of that, okay, much like the standard deviation, taking the square root of the variance, will bring it back into units that are familiar to you, right? This is especially useful for units that don't make sense when you square them. So for example, money, if you talk about the residual being $23, that makes sense. But then the squared residual, whatever 23 squared is, your residual, your squared residual is in square dollar, and I don't know what a square dollar is. Okay. So anyway, the values that minimize the mean squared error are going to be the same values that minimize the root mean squared error. So so that's just another option there. All right. Okay, so let's get back to this. It should be divided by capital N, not small n, right? Oh yeah, right here it should be divided by capital N. Sorry about that. That's a typo here. You are correct. Okay, yeah. I have the capital N here. Yeah. Thank you. Okay, let me jot that down. Slide 14. Let me just write slide 14. That is a typo. Okay. And I'll have to fix that. Okay. All right, so our linear model has two parameters, W0 and W1, the intercept and the slope. And when we make the prediction, the predicted value by the line is going to be W0, the intercept, plus the slope times X, okay? W1. Whoops, I wrote to the wrong person, okay. Okay. So if we plug this thing into the loss function, so this is where we've defined our loss function, this is what we're going to get. We're going to get 1 over n, t sub n minus the value we predict, w0 plus w1 x sub n squared, okay? So this is where we are. And what we want to do is we want to minimize, we want to find the value of w0 and w1 that is going to minimize this loss function. So this is our loss function, and we want to minimize this. Okay, maybe I'll just take a moment here. Give me a green check mark yes in your participants panel if everything is okay and this is all making sense to you. If anything is not making sense, or if I'm going too fast or something, give me a red no. Okay, and we can go back and just kind of take a moment to there. So I just want to kind of check in. Someone's saying go slower. Okay. All right, but I'm getting a bunch of green check marks, a bunch of yeses for this is okay. I got a once go slower, so so I'll keep that in mind as well. Okay, so thank you guys for your feedback there. Okay. All right, despite the request for going slower, this part, I am going to assume that you guys covered this in 100B, okay? I asked the last class and they indeed confirmed this. That in 100B, you had to derive the solutions for ordinary least squares regression, that you found the values for W0 and W1 that were going to minimize the total sum of squares or mean squared error, things like that. And you did that by using partial derivatives, right? So, so let me know if that's a mistake. Give me a red X if that is not true. But I think in 100B, you guys had to derive the solutions for least squares regression by taking this function or something similar to it and using the partial derivatives. Okay, so. So just kind of a quick review of what you did in 100B is that you treated the observed data, that is your X and your output T, as fixed, okay? And in that case, the loss function is going to depend only on your values of the intercept and the slope. And you wanted to find the values of those arguments, W0 and W1, that would minimize that loss function, okay? And those values that minimize it would be W0 hat and W1 hat. Okay, and so you'd multiply this out, you expand this out, you get this whole thing, and then you'd find the partial derivative of the loss function with respect to W0, and you find the partial derivative with respect to W1. You set those partial derivatives equal to 0, and you solve for W0 and W1, and that's how you came to the conclusion and say, okay, this is the value that's going to minimize the sum of squared residuals, right? And so I skipped a lot of the work, okay? Because, well, one is that it's written in the textbook, all detailed out, and the other is that this should have been covered in 100B. Okay, and so you have the partial derivatives, you set these equal to 0, and then you solve, and that will give you the estimates of W0 hat and W1 hat. Okay, what I'm going to do is that we are now going to work in linear algebra. Okay, and the reason for that is that these partial derivatives have these summation signs. The loss function itself has a summation sign, and the summation signs can get a tiny bit annoying to deal with. And so by working in linear algebra, when you do matrix multiplication in linear algebra, the summation is implied in the multiplication, right? So if you have a vector, a row vector and a column vector, a row matrix and a column matrix, when you multiply that row by the column, you're going to multiply, the first element and the, and the first thing, and you go to the next and you go down like this. And the matrix multiplication implies the summation, because you're going down the terms and then you add them up, and that forms the summation goes in there, right? It might have been a while since you took linear algebra. Maybe some of you guys took 115A, the proof-based linear algebra course, which I highly recommend if you're planning on going to grad school, but it's not a requirement for this class. Everybody did take 33A, at least your introductory linear algebra course, and maybe you took that your freshman year or something, or maybe it's been a while since you've taken it. So so please dust off your matrix linear algebra notes, and I also highly recommend this playlist on YouTube. Okay, this is a playlist from 3 Blue 1 Brown, which is an excellent YouTube channel. Everybody should subscribe to that. He produces these beautiful mathematics videos, and and all of the animations on there are actually coded in Python, and it's quite remarkable what this person's able to do. But 3 Blue 1 Brown, definitely highly recommend this this thing. I rewatch these videos frequently. These are it's like rereading a good book, or rewatching a good movie. This is what I like to do. So anyway, watch this linear algebra playlist, especially if you've forgotten, like what exactly is a determinant, and what all of that means and stuff. What's the cross product and dot product and things like that. So watch that. Very good stuff. Okay. And so what we're going to do is we're going to look at ordinary least squares regression, but we're going to approach it from a matrix with matrix notation. Okay. And so we're going to start here. So rather than having a separate slope and intercept value, we're going to combine them into this vector W. Okay, so the vector W right now is the intercept W0 and W1 combined. We've got a 2x1 matrix, 2 rows, 1 column. Okay, and then a single observation xn, we are going to append a value 1 to that. Okay, we're gonna have a 2x1 matrix here. So one observation. So if you think of this as like year predicting the time, okay, if the Olympics were in the year 1950, or I don't know, 1948 or whenever it was, okay, 1948, okay, this would be this xn would be 1948 appended with a 1 on top, okay, and that would be one observation, okay. And the reason why we need to have this 1 is that therefore we can express the prediction line being W0 plus W1 xn. We can express this as the product of the vector W times xn. So we're going to have W transpose multiplied by that value xn, okay? And so when you transpose W, it's going to become 1 by 2, and this is 2 by 1, okay? So you got a 1 by 2 matrix times a 2 by 1, and those dimensions line up, and this will result in a 1 by 1 prediction, okay? All right, so this is just one x value. And what we can do is we can say all of our x values together will be this matrix big X, okay? The matrix big X is going to be a column of ones and a column of all of the x values, okay? So we're going to have 1, x1, 1, x1, 1, x2, all the way down to 1, xn. So the big X matrix is going to be n rows, 2 columns, okay? A column of ones and a column of x's, okay? This is a n by 2 matrix, okay? And then the actual values themselves, the actual values um, is a column, an n by 1 column matrix, okay? We've got n actual values, and that's going to be here, a column of n values, n by 1, okay? And if we have this notation, then the loss function, okay? So the loss function being our mean squared errors, right? So if we scroll back to here, this is what we have, the mean squared errors, or the squared residuals. So the difference between t and our prediction, this quantity squared summed up divided by n, that can be expressed as this matrix multiplication, no summation sign, okay? And so let me just kind of show the work on how we get there, okay? So the column matrix, okay, X is n rows, 2 columns, okay? And then the intercept and slope is in this W matrix, okay? 2 rows, 1 column, okay? And so I can multiply X by W. XW is going to be this, okay? So here's our X matrix and here's W. And therefore, I would do 1 times W0 plus X1 times W1, and we get this first value, W0 plus W1 X1. And the next thing is 1 times W0 plus X2 times W1, W0 plus W1 X2, okay? And this is going to form our predicted values, okay? Which is going to be basically n by 1 matrix, okay? N rows, and there's only 1 column here, right? Now, you might, as you are doing stuff, okay, especially when you're starting out, you might get confused. Do I write X times W, or do I write W times X, okay? Now, in regular old algebra, it didn't matter when you did X times W or W times X. If they were just single values and you multiplied them together, it didn't matter. Multiplication was commutative. The order that you did it didn't matter. But when you do matrix multiplication, the order is very important, right? And so what has to happen is that the dimensions have to line up, okay? And so to kind of ensure that your dimensions line up, I strongly recommend writing the dimensions of these matrices underneath these things, especially when you're doing it on paper. Say X is an n by 2 matrix, okay? Number of rows followed by number of columns. N by 2 matrix. W is a 2 by 1 matrix, okay? 2 rows, 1 column. And therefore, I can multiply X times W, okay? Because these inner things, the number of columns in the first matrix matches the number of rows in the second matrix, okay? And therefore, when I multiply these, I'm going to get n by 1. If I tried to switch it around and I did W times X, I would have a 2 by 1 multiplied by an n by 2. And that's not going to work, okay? Because it always has to be the number of columns in the first matrix has to match the number of rows in the second matrix, right? So these inner dimensions, the 2 and the 2 must always match, okay? So if you wanted to do something like this in R, okay? So here I've taken our Olympic data. I've taken the column year, okay? And so I've got, I think there's 28 rows there, okay? N is 28. I'm going to repeat the number 1 28 times, okay? And I bind the ones with the X, okay? And this is gonna produce my matrix X. So matrix X is 28 by 2, 28 rows, 2 columns, okay? And W, I'm just going to make a matrix with 2 rows and 1 column, okay? And so W is 2 by 1, right? And so I can take X and do matrix multiplication. This is the operator for matrix multiplication, X star percent W, okay? and that works. I get a 28 by 1, right? If you do it the wrong way and you do W times X, W matrix multiply X, you get an error here, okay? And the error you get is non-conformable arguments, right? So I'm going to be a little presumptuous, but I'm going to predict that in your homework, when you do your homework, that you eventually will probably come across a non-conformable arguments error at some point, okay? And that means you are likely doing some kind of matrix multiplication where the dimensions do not match up, okay? And so always, I strongly recommend doing writing down the matrix operations that you're going to do on paper, and underneath each of your matrices, write the dimensions of each thing. And you always want to make sure that the inner dimensions line up, okay? Because if they don't, you're going to run into this problem, right? And so it's always helpful to know what exactly your errors mean, and non-conformable arguments mean that you've done some kind of matrix multiplication and the dimensions don't align. Okay, so we go back. So here we've got, we said our predicted values, okay, can be expressed as xw, okay? And therefore, the residuals can be expressed with this, t minus xw. T minus xw is going to be an n by 1 matrix, right? T is n by 1. We've got n values, and it's just a column. It's an n by 1 column matrix. T is n by 1. And xw, after we take x, which is n by 2, and w, which is 2 by 1, xw is n by 1. And so t minus xw is also going to be an n by 1 matrix. Okay, so this is just one column of values here. All right, and so when you do addition or subtraction, the dimensions also have to align. All right, and so when we talk about the sum of squared errors, okay, when we say the sum of the residuals or the errors squared, okay, we can take a look and we can say, okay, each value in here, okay, if I take t minus xw and I transpose it, I'm going to get this, t minus, the quantity w0 plus w1x1, and followed by t2 minus the quantity w0 plus w1x2, so on and so forth, all the way up to tn. And the column is still this. And we can see that when I do this matrix multiply, I'm going to do this times the first value, the second value times the second value, all the way to the nth value times the nth value. And because of matrix multiplication, the summation is implicit. Okay, the summation is performed inside this matrix multiplication. So I no longer need to write the sum function. Okay, and here I can just write this. And so our squared errors, sum of squared errors is going to be t minus xw quantity transpose times t minus xw, okay? And t minus xw transpose is a 1 by n matrix multiplied by an n by 1 matrix, t minus xw. And therefore, when I multiply these two things together, I'm going to get a 1 by 1 scalar value. Okay? I get a 1 by 1 scalar value. I can multiply that by, or divide by n, which itself is a scalar value. And so the loss function is a 1 by 1 scalar value, which is exactly what we want. That when we go through this process of figuring out the sum of squared errors, we're getting just one value, right? When you calculate the total residual sum of squares or the mean squared error, you're just getting one value. You're not getting a vector of values, okay? And indeed, we can see even with our matrix notation, we get a single squared value. All right. Okay, if this is good, give me a green check. Let me know that that you're following along. Or give me a red X if this is no good, before I go on to the next slide. Okay, all right, well, thank you to those of you who responded. So far, I've got a bunch of yeses, about 40, 42. Some of you have not responded, but but nobody's given me a no yet, so I'll take this as a good sign. Okay, and so what we want to do is we're going to expand this, okay? So I've got t minus xw transpose times t minus xw. This is our loss function. And I'm going to expand this. I'm going to do t minus xw transpose times t minus xw. And so I don't know if you remember all of your linear algebra and matrix multiplication rules, but again, you're going to have to probably dust off some of your notes to kind of look at this. You can distribute the transpose, and you're going to get t transpose minus xw transpose, t minus xw. And then when you distribute the transpose over a product, it actually reverses the order of that product. So xw transpose becomes w transpose x transpose, okay? And so we've got this, right? T transpose minus w transpose x transpose times t minus xw. Oh, let me give you the answer to the second attendance quiz question. The second quiz question's answer is D as in dog. D as in dog for the second quiz question, okay? D as in dog. All right, and here we are. And just kind of in the interest of time, I think I've detailed all of this out quite well. And so I'm going to kind of just go through this, fairly quickly. But underneath each of these things, again, I've written the dimensions of each of these things. So T transpose is going to be 1 by n, and T is n by 1. And so when I multiply T transpose by T, a 1 by n by an n by 1, that's going to give me a 1 by 1. Okay? T transpose xw is 1 by n by n by 2 by 2 by 1, okay? And again, the inner dimensions all line up, so that works out, and this simplifies to a 1 by 1, okay? And similarly, you got w transpose x transpose t, and I got w transpose x transpose xw. And if you follow all of the dimensions, and it's a good exercise to do it, you're going to get 1 by 1, okay? And so all of this is a 1 by 1 thing. And I can actually combine these two, T transpose xw and W transpose x transpose T. These are transposes of each other, right? So if I take this and I transpose this, it reverses the order, and we're going to get this. And because it's a 1 by 1 scalar, the transpose of a 1 by 1 scalar is itself. And so I can combine them, okay? So anyway, all of this to say, our loss function, when I expand it out, is going to look like this. Okay? T transpose T minus 2 W transpose X transpose T plus W transpose X transpose XW. Okay, that's a lot to say. And this is just on the previous slide, the comment about being able to combine the two together because they are transposes of each other. All right, so this is where we are, is that we have defined the loss function in matrix notation. That's a great step, okay? We don't have any summation terms in here. It's all just in matrix notation. This is the total, or the mean squares error, mean squared error, without any summation signs. So it's in matrix notation. And what we want to do is we still want to minimize this thing with respect to W, okay? We want to find the value of W that is going to return the smallest mean squared error, all right? And so what this is going to do, in order for us to do this, is we're going to take the derivative with respect to the vector W. Okay, so rather than dealing in partial derivatives, we're going to take the derivative with respect to W. We're going to set that derivative equal to 0, and then we're going to solve for that matrix W, okay? And so to do this, we have to delve into a little bit, just the tiniest bit of vector calculus, okay? Vector calculus, very complicated subject that I barely know anything about, but I know just enough to get us through this section, okay? All right, so just a quick review of derivatives, okay? So you have a univariate function which takes one input x, outputs a y, it maps from the real space to the real space. And the derivative, f prime at x, can be thought of as, you're adding some small quantity h, and you're taking the difference of f of x plus h minus f of x divided by h as h goes to 0. Okay, and if you rearrange some terms, and if you multiply both sides by h over h or something, like if you try to bring this over here, you can also say that it's going to be the solution to this, as f prime of x is going to solve this thing where this quantity is equal to 0. Okay. In the when we talk about the gradient, what we have is we have a function that maps from n-dimensional space to a single number. Okay, so this is our loss function. Okay, we're going to treat the t as fixed. We're going to treat the x values as fixed. Okay, those are fixed values, and therefore this function, this loss function, is a function only of w. W is the only thing that's allowed to vary in this function. Okay, w is a vector that exists, is a vector of length 2. It's a two-dimensional vector. All right, so the input is the vector w, okay, or matrix 2 by 1 matrix w. It's n-dimensional, but the output of the loss function is a single scalar value. Okay, so it goes from n-dimensional real space down to one-dimensional real space. It goes from a two-dimensional vector down to a single scalar output. And the gradient of this function at some location x, okay, the gradient of f at x is basically the multidimensional derivative. Okay, it's going to satisfy this equation. Practically speaking, you can think of the gradient with respect to, of a function with respect to a vector w as the vector of partial gradients. Okay, so this kind of works out. Okay, so we've got the gradient of f with respect to w. You can think of it as the vector of partial derivatives. Okay, vector partial derivative of each component of w, and it's going to be kind of the vector of that. All right, and so just one geometric interpretation of the gradient. Okay, so the derivative can be the slope of the tangent line. The gradient is going to will point in the direction of the greatest rate of increase. So if you have some, surface, the function represents some kind of surface in a higher dimension, the gradient points in the rate of steepest descent, or greatest rate of increase. Okay, and this is going to be the last slide I get to today, but I just want to kind of cover some of these useful gradient relations, and I realize I'm 1 minute over my time here, but just stick with me. Okay, so keep in mind that f results in a single scalar output value. Okay, and we're going to take the derivative, or the gradient of f, with respect to the vector w. Okay, so w transpose x, this implies, if you think of what w is, w being like 1 by n, okay, w transpose times x, x has to then be n by 1 because the output has to be 1. The gradient of this is going to be x. So the gradient of f with respect to w is going to be a vector, n by 1, okay? And so w transpose x, the gradient of that with respect to w is x. X transpose w, the gradient of that with respect to w is x. If you have w transpose w, which is, you can think of this almost as like w squared, okay? So it almost kind of makes sense. There's a lot of analogs between this and regular old univariate calculus. So if you think of this as w squared, the gradient of that is going to be 2w, okay? And then here I've got some matrix C. I've got w transpose CW, okay? Now if w is n by 1, okay, which means w transpose is 1 by n, okay? What are the dimensions of C, okay? What are the dimensions of this matrix C? I just want to kind of make sure that we're all on the same page here. So go ahead and type in the chat what you think the dimensions of the matrix C are. Yeah. Okay, so some of you guys got it right away. Yes, the matrix C is going to be an n by n matrix, right? And if it's anything else, the dimensions are not going to multiply or work out and so the dimensions are going to, multiplication is going to fail. So C has to be an n by n matrix, okay? If W is n by 1 and W transpose is 1 by n. So, so we are going to leave off here. We'll pick up right here on slide 35 on Friday. And basically, now that we've got just the basic tools of doing some derivatives with respect to gradients, what we can do is we can take this loss function and we are going to take the gradient with respect to W. We're going to solve for where that is equal to 0, and that will give us the solution for what W is going to be. Okay, am I going to upload the slides? Yes, I will upload the slides. Okay, and yeah, take the time. Okay, what was the answer to the second quiz question? The answer to the second quiz question is D as in dog. D as in dog. Okay, have a good day. Stay safe out there, and we will see you guys on Friday. Okay. Oh, actually, I have to stop.